guys, this is Alma M. Magallanes and I'm going to discuss about transcendental and polynomial equation and iterative bracketing method. Iterative bracketing has two methods, which is the bisection method and the regular falsi method. So, what is the bisection method? The bisection method is a successive approximation method that narrows down an interval that contains a root of the function. The bisection method is given an initial interval that contains a root. That we can use the property sign of f of a is not equal to the sign of f of b to find such an initial interval. The bisection method will cut interval into two halves and check which half interval contains a root of the function. The bisection method will keep cut the interval in halves until the resulting interval is extremely small, and the root is then approximately equal to any value in the final or the very small interval. Next, we have here an example of a bisection method. Bisection method. Find the root of the function that is given, which is x cubed plus 3x minus 5. First, we will find the interval from substituting 0 to the function, and f of 0 is equals to negative 5. Negative 5 is lesser than 0. And take note, in finding the interval, its answer should lie in between negative and positive, and it should be in the closest one. F of 1 is equals to 1 plus 3 minus 5 is equals to negative 1, which is lesser than 0. And f of 2 is equals to 8 plus 6 minus 5 is equals to 9. So, negative 1 and 9 is the closest one. So, our interval will be 1 and 2. And in the interval, the A will be 1 and
Next,
the B will be 2.
we have the second method of the iterative bracketing method, which is the regular falsi method. Regular falsi method is a numerical procedure for solving an equation in an unknown is the regular falsi procedure or false location method. It is very similar to the algorithm of the bisection process, which is one of the oldest methods. It has been generated because the process of bisection converges at a very slow pace. In basic words, the approach is the trial and the error process of using the variable test values and then changing the test value according to the result. The false location method, abnormal falsi, is used in problems involving arithmetic or algebra to apply to simple trial and error methods of solving problems by replacing test values with unknown quantities, and this is sometimes also referred to as the guess and check prop. Now, I have here an sample problem for the regular falsi method. Regular falsi method. Find the root of function f of x equals x cubed minus x minus 1 up to 3 decimal places. In finding the roots, first we are going to find the interval, starting from substituting numbers to function, and we're gonna start from 0. Take note, in finding the interval, the answer in the function should be a succeeding negative and positive. Let's start. F of 0 is equals to 0 cubed minus 0 minus 1 is equals to negative 1. F of 1 is equals to 1 cubed minus 1 is equals to negative 1. F of 2 is equals to 2 cubed minus 2 minus 1 is equals to 5. So, now, we have here the succeeding negative and positive answer. And our interval is 1 and 2.
Will be negative 1.
Our A here is 1 and the
B will
is equals to 2.
The B to the
Now,
function,
let's find the
and
root.
it will be 3.
Here is a table in which you can find the number of iteration
midpoint, we are going
f of
to
A, f
add
of B,
A plus B
x,
over
and f of
2,
x. Take note
1
that we
plus
should
2
stop if the first
is equals 3 divided by 2,
is being
1.5.
repeated because
And
that
in
is
finding
our
the
root.
f of c, in
finding the root, we have here the formula. X is equals to A times f of B minus B times f of A over f of B minus f of A.
1, which is 1.
On the first iteration, our A is 1 and the B is 2, f of A is equals to negative 1, f of B is 5. Our x here in this x, we are going to use the formula that I have mentioned before, and the answer is 1.167. The f of x is equals to negative 0.579. Since our f of x here is negative, we are going to change the value of the next iteration of a and the f of a, and the b and the f of b will still the same. And if our f of x is going to be positive, we are going to change the b and the f of b, and the a and the f of a will still remain the same. So now on the next iteration, our a now is the previous x, which is 1.167. The b is equals to 2, and the f of a is the previous f of x, which is 0.579. The f of b is 5, and the value of the x here we're going to use the formula that is being used, that is 1.253. The f of x is 0.285. Since it is negative again, we are going to change the a and the f of a.
Let's proceed to the third column. Since our f of c here is positive,
the b
our
is
a
2,
will be the same,
f of a
which
is
is
negative
1, and the b will be
0.285, f of b
1.25
is equals
because the
to
previous
5,
c
x
is
equals
also
to
1.25, and the f
1.293, f
of
of
a
x negative
will be negative 1, the f of
0.129.
b will be
Fourth iteration
0.703,
1.293, b is
our
equals
c
to
is
2, f of a is negative
1.125, and the f of
0.129,
c
f of
is
b
equals
is
to
5, x is
0.201,
1.311,
and
f of
our
x
b is
is
equals
equals to
to
negative 0.057.
0.75.
The fifth
Let's proceed to the fourth
A is equals
column.
to
On the
1.311,
fourth
b
column,
is
since
2,
our f of c
f of a is negative
the a will be
0.057,
changed,
f of
and
b
the
is
a will be
equals to 5, x is
1.125 because the
1.319,
previous c is
f of x is
1.125,
negative
and the b will still be the same,
0.243.
which is
On the
1.25.
sixth
The f
iteration,
of a will
a
be
is
negative
1.319, b is
0.201,
2,
f of
f
b
of a
is
is negative
0.703,
0.0243, f of
c
b
is
is
equals to
5, x is
1.1875,
1.322,
f of
f of
c is
x
equals
is
to
negative
0.237,
0.0103.
b
On
minus
the
a is
seventh
equals to
iteration, a is
0.125.
1.322, b
On the
is
fifth
2, f
column,
of a is
A
negative
will be 1.125,
0.0103,
B
f of b
is
is 5, x is
1.1875, f of A is
1.3236, f
negative
of x is negative
0.201, f of B is equals to
0.0044. On the
0.237,
eighth
C is equals to
iteration, a is
1.1625, f of C is
1.3236, b is 2,
0.014,
f
B
of a
minus
is
A
negative
is
0.0044, f
0.0625.
of b is 5, the x is
The next iteration, since our f of c
1.3248,
is
the f of
positive, the
x
b will be
is
changed. So A is equals to
0.00187, the a
1.125, B is
is
equals to
on the next
1.15625,
iteration is
f of A is
1.3242.
equals
If
to
the b
negative
is 2, f of a
0.2001,
is
f
negative
of B is equals to
0.00187,
0.014,
f of b
C
is
is equals
5,
to
x is equals to
1.1406, f of C
1.32453,
will
f
be
of x
negative
is equals to negative
0.034, B minus
0.0079.
A is equals
The
to
next iteration, the a is
0.03125. Since the f
1.32453,
of C is
the b
negative,
is
the
2,
A will
f
be
of
changed.
a is
So A is
negative
equals to
0.0079,
1.1406,
the f of
B
b
is
is
equals to
5, the x is
15625, f of A is equals to
1.32464,
negative
the f of x
0.04,
is negative
f of B
0.0034.
is
And
equals
we
to
are going to stop here
0.014,
because as
C
you can
is
see,
equals to
the first
1.144,
three
f of
decimal
C is
digit
equals to
of
negative
the 10th
0.040,
iteration and the ninth
B minus
iteration
A
is
is
the
equals
same,
to
which or being repeated,
0.0156.
which is
Since
1.324.
0.0156 is almost
So
to the
since
value which we
it
are
is
going to
being
stop, which
repeated,
is
that the
0.01,
so the
and we are going to
approximate
take
root
this
of the
here.
function f
And
of x
since the
is
f of
equals
c
to
here
x
is
cubed minus
negative,
x minus
our
1
value
is
of a in the next iteration will be changed,
1.324,
and it
and
will
that
be
is our
so
answer.
a in the next iteration is
Next, our topic will be the
1.484, and
iterative
the b will be the
non-bracketing
same,
method
which
or
is
open method.
1.15625.
Now, I have here two
A
of
is
the
equal, f of A is equals
non-bracketing
to
method, which are
negative
the Newton method and the
0.040,
second
f of
method.
B is equals to
Let's start
0.014,
from
and the
Newton-Raphson
C
method.
is equals to
The
1.1523,
formula in which we are going to use in
are going to
Newton-Raphson
solve first the
method
B
is
minus A
x
if
nu
it
is
is
equals to
lesser than
xa minus the function of
0.01.
xa
So
over
B
the
minus A is
derivative
equals
of
to
the function of xa.
0.0078.
Here's an example in
Since
finding the Newton-Raphson method. Find
0.0078
the
is
root of an
lesser than 1,
equation
where
f of
we don't
x
need
is
to
equals
solve
to
for the
x
f
cubed
of c.
minus x minus
And
1.
since the
Now,
b
the
minus
first
a
step
at
that we
b
are
is
going to
equals
do
to
is find the interval.
1.1562
Starting from
is greater
0,
than
we have
0.01.
here the
Therefore, the
interval
approximate
1 and
root of
2.
the function given is
Next, we are going to find the
1.1562.
root that lies between the 1 and 2. And that root is we are going to need it to start the first iteration. So, in order to get the root, we are going to divide the interval into 2. So, we have here 1 plus 2 and divided by 2 is equals to 1.5. And the next step, we are going to substitute the 1.5 to the formula that I have mentioned. And that is xa minus f of xa over the derivative of the f of xa. Our function of x here is the x cubed minus x minus 1, and the derivative of it is 3x squared minus 1.
Upon substituting the 1.5, I have here the table which shows the number of iteration and its answer. So on our first iteration, our xa is 1.5 and the function of xa is 0.875 and the function of fxa is 5.75. And our x now is 1.3478 after answering the formula. So the x now will become the new xa, which and the HA is 1.3478 for and the second iteration, and the f of xa is 0.10068 and the derivative of fxa is 4.449 and the x is 1.3252. On the third iteration, the x will go to the xa, which is 1.3252 and the f of xa is 0.00206 and the derivative of fxa is 4.26847 and the new x will become the 1.32472 and the new x will become now our xa, which is 1.32472 and the f of xa is 0 and the derivative of fxa is 4.2646 and the new x is 1.32472. Now we are going to stop here because the two successive iterations are being repeated, which is 1.32472. So therefore the approximate root of the equation x cubed minus x minus 1 is equals to 0 is 1.32472. That's all for the Newton-Raphson method. Now our next topic is the second method. Here is an example for the second method. Find the root of an equation f of x is equals to x cubed minus x minus 1 using the second method. The first step that we are going to do is to find the interval. Starting from 0, we have now the interval 1 and 2, which a as 1 and b is equals to 2. And the next step we are going to do to find the root is use the formula. Our formula in second method is x nu is equals to xa minus f of xa times xa minus xb over the function of xa minus the function of xb. Now we have here the table which shows the iteration, the xa, xb, the function of xa and the function of xb. On the first iteration, we have here the xa, which is 1, xb, which is 2, the f of xa, which is 1.167, and f of xb, which is negative 0.5787. Next, on our second iteration, our xa here will be coming from the previous xb, which is 2, and the xb will be coming from the previous f of xa. And now, here in our fxa, we are going to use the formula that I have said before. After substituting it to the formula that I have mentioned before, we have now the f of xa, which is 1.253, and the f of xb is negative 0.285. On the third iteration, we are going to repeat the process that we have done in iteration 2. Our xa now is 1.167, xb is 1.253, f of xa is 1.337, and the f of xb is 0.0539. And on the fourth iteration, our xa is 1.253, xb is equals to 1.337, f of xa is 1.324, and the f of xb is negative 0.003. We are going to stop here now because the value of the f of xa in the fifth iteration is the same as the fourth iteration. So therefore, the approximate root of the equation x cubed minus x minus 1 equals 0 using second method is 1.324.